Okay, so today we're going to be going over section 9.9. In section 9.8, we talked about power series, and what a power series basically is an infinite polynomial. And so today we're going to be going over one way of writing a function in power series form, representing that function by a power series. That's why it's called representation of functions by power series. In this section, we're going to be focused on using the geometric series. And so we know that when you have a geometric series, your series will converge if the absolute value of your common ratio is less than 1, and it will diverge if the absolute value of your common ratio is bigger than or equal to 1. And so we have this result. The series converges to the sum a over 1 minus r as long as your common ratio has an absolute value that's less than 1. Okay, so I've written the geometric series here. I've expanded it out rather than writing it in summation notation. And it says, find the power series formed by the substitutions a equals 1 and r equals x, and give a closed form formula for the power series and the interval of convergence for the power series. So if we take our geometric series and we replace a with 1, well then our first term will be 1. And we're replacing the r with x, so our second term will be x, and then x squared, and then x cubed, and so on. And so then we can use this formula right here to write a closed form formula for this infinite sum. It's going to be the first term, 1, over 1 minus the common ratio. And so what we've just done here is for the function f of x equals 1 over 1 minus x, we have written it in power series form as 1 plus x squared plus x cubed plus dot dot dot. But this power series only works as long as our common ratio is less than 1, which means that the absolute value of x, which is our common ratio, needs to be less than 1. Our common ratio, if you divide any term by the term before it, you get x, and so the absolute value of our common ratio needs to be less than 1. And so then that means then that negative 1 is less than x, which is less than 1. So that means that our interval of convergence is from negative 1 to 1, and right in the middle of negative 1 to 1 is 0. So this is centered, this power series is centered at 0, right? So it's one of the things you need to get comfortable with is what do they mean by centered at 0? It means that your interval of convergence, right in the middle of these two endpoints here, is whatever is where it's centered at. Also notice that when it was centered at 0, it was a polynomial in x. So that's also going to be important. Let's do one more of these. Try this one on your own. Pause the video and see if you can't get this on your own. Okay. Oh, before I do that, I'm sorry. Now, if you look at the function 1 over 1 minus x, the only number that we cannot substitute into this function is 1. We can substitute in any other number. But in the power series representation, we're only allowed to use numbers between negative 1 and 1. And so then if we wanted to represent this function by a power series for some number outside of that interval, we would have to go and create some other power series for that, and that's one of the first things we're gonna be doing here. Okay, so again, try and pause this. Try and do this on your own and pause it. Pause the video. Try it on your own. So this says find the power series formed by the substitutions a equals 1/2 and r equals x plus 1 over 2, and give a closed form formula for the power series and the interval of convergence for the power series. So again, the power series you get just by substituting into the left side. And so when you're putting in a half for A, your first term is a half, plus a half times x plus 1 over 2, plus a half times x plus 1 over 2 squared, and then plus dot dot dot. And we can write this in summation notation. Summation, every term has a half in it, and we could bring that half over here. And every term has an x plus 1 over 2. And then they all get raised. We started out with a 0. And it goes on forever, and this gets raised to the nth power. Then you should recognize this as a geometric series, and we can just, the closed form formula comes from this over here. And so then your first term is a half. 1 minus your common ratio, which is 1 minus the x plus 1 over 2. Now we can clean this up by multiplying the numerator and denominator by 2. And then what we get is 1 over 2 minus x plus 1. And these 2's will cancel out, but not the the parentheses don't go away because we still have that. And so then you get 1 over 1 minus x. So this is the same function that we had in our previous. We ended up with 1 over 1 minus x in our previous problem. But this series is the same function, but for a different interval. Because for here, your r, which the absolute value of your r, so the absolute value of x plus 1 over 2 needs to be less than 1. So that then means that the absolute value of x plus 1 needs to be less than 2. And so then that means that negative 2 is less than x plus 1, which is less than 2. And if you subtract 1 from all three sides, you get that negative 3 is less than x, which is less than 1. And so your interval of convergence is everything from negative 3 to 1. Okay. So this formula works for everything from negative 3 to 1, and you get the same out of the series as you get out of this function. But notice that the center of these right here is negative 3 plus 1 divided by 2, which is negative 1. So this power series is centered at negative 1. And you can tell that you're centered at negative 1 by the terms by looking at your variable part. Your variable part is not a polynomial in x, it's a polynomial in x plus 1, and the 0 of x plus 1 is negative 1. So that's how you're going to know what you're centered at. When you look at your terms, if they all have an x plus 1, whatever makes that 0, that's where you're centered at. Okay. And so now we're going to want to go backwards, right? Find a power series for f of x equals 1 over 1 minus x, same function again, but now we want to be centered at x equals negative 2. x equals -2 means that we want our polynomials, we want our polynomial in terms of x plus 2. So we want an x plus 2. So again, trying to walk you through this, I gave you the substitutions of what to substitute in over here, and then we figured out this one, and now we're going backwards. Now we're going to start with this and figure out what do I substitute in for A and what do I substitute in for R to get this right here. And then once I do that, then I can make my substitutions on the left. So that's a little strange. What we have is 1 over 1 minus x. We know that we want it in terms of x plus 2. So here's how I'm going to do that. So I have 1 minus, and I'm going to put parentheses, and x. Now, I haven't done anything at all right now other than put those parentheses. So I have the exact same expression. But inside those parentheses, I want a plus 2. So I'll put a plus 2 over here. But that changes the problem. When I distribute, that plus 2 actually is a minus 2 because we've got this minus over here. When you distribute it, this becomes a minus 2. So to undo that, I'll add 2 over here. Right? Now you can go ahead and distribute and see that you get the same thing. 1 minus x minus 2 plus 2. These will go away and you still just get your 1 minus x. So these are truly exactly the same. Right? So I haven't changed the problem. You need to make sure you don't change the problem. And so then this becomes 1 over, now we can combine the 1 and the 2 to get 3. Minus x plus 2. Okay. Now, so what we're doing now is rather than substituting into the left like we did in the first problem, we want to figure out what we substitute in here, right? So we want to make this match. We want this right here to match what I have there. And on the top could be any number. That's going to be your value of A. But on the bottom, you need this to be a 1. And so the only way we can make that a 1 is, again, using basic arithmetic. Multiply the numerator and denominator of this fraction by 1/3. And when I do that, I get 1/3 divided by 1 minus x plus 2 over 3. And now you can see that you have the exact same thing. It has the same form. It has the same form. You have a number in the numerator, 1 minus a number in the denominator, and the number that you are minusing is your common ratio. So what you are going to substitute in for R is this x plus 2 over 3, and what you are going to substitute in for A is this 1/3, right? And so then when you go in and you do that, then you go to the left side and you substitute these in. So you get 1/3 plus 1/3 times x plus 2 over 3 plus 1/3 times x plus 2 over 3 squared, and so on. And you can write it in summation notation. A summation from n equals 0 to infinity of every term has this 1/3, and every term has this factor of x plus 2 over 3 raised to the nth power. And so now what you have is a power series representation for 1 over 1 minus x, right? And the interval of convergence, well, that will converge when your common ratio, this x plus 2 over 3, x plus 2 over 3, absolute value, it needs to be less than 1. which means then that -3 needs to be less than x plus 2, which needs to be less than 3. And if you subtract 3, then -5 needs to be less than x, which needs to be less than, I'm sorry, if you subtract 2, then -5 needs to be less than x, which needs to be less than 1. And you can see that right in the middle of these, -5 plus 1 is -4, divided by 2 is -2, so it is centered at -2. That is what that means. Also, your polynomial is in terms of x plus 2, right? So if it's centered at x plus 2, then it needs to be a polynomial in x plus 2. -2 is what makes that 0. Okay, let's do another one. Pause the video, try and do this on your own, and then resume the video. It's the only way you're going to get good at this. Just watching me do this is just going to be boring. And try it. Maybe you don't get it right. Maybe you do, and then you feel really good about yourself. But just sitting here watching me do this is not that great. Okay, so find a power series for f of x equals 1 over 1 minus x, centered at x equals 2. Centered at x equals 2 means that we want our polynomial to be in terms of x minus 2. So we want our r to have some expression that looks like x minus 2. Okay, so what we have is 1 over 1 minus x. Again, 1 over 1 minus, very first thing I'm going to do is just put that x inside the parentheses and, leave some room in case I have to add something, or when I add something, I should say. Now, I haven't done anything yet. These two really are equal, but I wanted an x minus 2, so I have to subtract 2 here. But then what did I really do? Because this gets distributed to here, that makes it plus 2, so over here I have to undo that, minus 2. Okay, and so I do and I undo. So let me go ahead and change the color there. So I have to minus 2 so that I get my x minus 2. And then I have to, when I distribute, I would get a plus 2. So over here I have to undo that. So I have to minus 2 as well. And now things are looking good. Okay. So then, so these two really are the same now, and we can move on. But we're going to combine the 1 and the -2. That makes -1. But the formula requires that I have a positive 1 there. So if I just multiply the numerator and denominator by -1, then I will make that first term a -1. And when I do that, I get a -1 in the numerator. That's my a. And the first term is 1. And then I have this extra factor of -1. Now, in algebra, you would have just made this a plus, but I want to make it match this minus, so I left it minus and left that a -1. And so then you could see that your a is -1 and that your r is -1 times x minus 2. Right? That is what this part is. And so then first term is -1, and then your -1 times the -1 times x minus 2, and then a -1, and then -1 times x minus 2, and the whole thing is squared. And then you still have that negative 1. And then you have the negative 1 times the x minus 2 cubed, and so on. And you can write that in summation notation from n equals 0 to infinity of, they all have this negative 1, and then the negative 1 gets raised to the n power, and the x minus 2 gets raised to the n power. And so then we could rewrite this, because these have the same base. We can rewrite this as the summation from n equals 0 to infinity of negative 1 to the n plus, to the n plus 1, x minus 2 to the n. This is geometric. You get from one term to the next by multiplying by x minus 2 times negative 1. And so then it converges when your common ratio is less than 1. So there you go. Okay. So in exercises 3 through 6, find a geometric power series for the function centered at 0 by the technique shown in example 1 and 2, and B by long division. You can look at your book, and your book tells you how to do this using long division. I'm not going to focus on that. You don't have to worry about that. So I'm not gonna ask you to do that. But if you're curious, you can look at your book. Okay, so again, the formula is that if you have a over 1 minus r, that comes from a geometric series. That comes from a plus ar plus ar squared plus dot dot dot. So we need to make the left side look like this. Okay, so again, we want this to be centered at 0, and so we already have the factor of x right there, so we're good there. The only thing is we need this to be 1, and so in this problem then we can just multiply the numerator and denominator by 1/5. And so then we get 2/5 over 1 minus x over 5. By writing it like that, you can see that your a is 2/5 and your r is x over 5. And so then your power series is a 2/5 plus 2/5 times x over 5 plus 2/5 times x squared over 25 plus 2/5 times x cubed over 125, and so on, which you can write in summation notation, right? If you notice, you get one factor of 2, and the power on the x is to the nth power. In the denominator, you have powers of 5, and it's to the n plus 1, right? For the first term, you just have 1. For the second term, you have 2. For the third term, you have 3, and so on. And there you go. in exercises 7 through 18, find a power series for the function centered at C and determine the interval of convergence. Okay, so we want it centered at -2. That tells us we want a polynomial in x plus 2, right? So -2 is the zero of what you want your polynomial in, okay? And so then what you have is 2 over 6 minus x. You're trying to get to a over 1 minus r, but your r needs to have this expression of x plus 2 in it so that it's centered at -2. And so then again, first thing we do is we put parentheses around the x. That does absolutely nothing. But then I want x plus 2 here, so I plus 2. And then that becomes a minus 2, so then I add 2 over here to undo it. And if you distribute right now, the two expressions are exactly the same because the minus x minus 2 plus 2, the 2's will go away and we will be good. But we can now combine the 2 and the 6 and get 8. We're almost there, but we want a 1 there. So we multiply the numerator and denominator by 1/8. And so now we get 1/4 in the numerator. That's my a. And in the denominator, we get 1 minus x plus 2 over 8. And so then that is my r. And so then we put that into our formula. Now, we don't have to keep writing out the terms. We can just go to the summation formula from n equals 0 to infinity. And the first term is the a, the 1/4. And the common ratio is x plus 2 over 8 raised to the n. And there we go. That is it. Oh, we're also being asked to find the interval of convergence. So the interval of convergence, the common ratio is this x plus 2 over 8. So then x plus 2 over 8, absolute value, needs to be less than 1. So -8 needs to be less than x plus 2, which needs to be less than 8. So then -10 is less than x, which is less than 6. And if you add -10 and 6, that gives you -4 divided by 2 is -2. So the center of this interval, that's how you find the center, -10 plus 6 divided by 2. That's how you find the middle of an interval. And that is -2, so it's centered at -2. But these are the values of x that you can put in here. This is your interval of convergence. Find the power series for the function centered at C and determine the interval of convergence. Okay, so again, we're trying to get to something that looks like this, a over 1 minus r, and this already looks like that. So then r, you can see, is 4x. Centered at c equals 0 means we want a polynomial in x, right? And so that's what we already have. We already have an expression in x for our r value. And so we're good to go. So r is equal to 4x. Our first term is 1. And so then this becomes the summation. Our first term is 1. We don't have to write a coefficient of 1. Our common ratio is 4x to the n from n equals 0 to infinity. Okay. And so then interval of convergence, this will converge whenever the absolute value of 4x is less than 1, which means 4x needs to be between -1 and 1. And then you multiply both sides by a quarter, you get -1/4 is less than x, which is less than 1/4. And right in the middle of those is 0. So the interval of convergence there, I'm sorry, the center is 0, which is where we wanted it centered at. Okay. Find a power series for the function centered at C and determine the interval of convergence. Okay. Again, we want to get to something that looks like this. And so then what we have is 4 over 3x plus 2. First thing I'm going to do is I'm going to rewrite it so that the x term is second. Nothing happening there, that's just algebra. Then I'm going to put parentheses around the x. Haven't done anything there. But centered at c equals 3 means that I need an expression in terms of x minus 3, so that 3 makes it 0. And so then we can just put the minus 3 there. But you need to be careful here. When you put that minus 3 there, let me go ahead and change the color on that. When you put that minus 3 there, there's this 3 in front that multiplies it. So what you actually did to the denominator is you included this new term of -9, and so you have to undo that by adding 9 over here. Now if you were to distribute and combine like terms, you would see that the two expressions are exactly the same. This expression and this expression are exactly the same. So this is 4 over, but we could combine the 2 and the 9 and get 11 plus 3 times x minus 3. And so 3x minus, if I distribute, I get 3x minus 9, and then the minus 9 and the 11 would give me the 2. Same thing. I haven't done anything, but I'm trying to get it to look like this. So again, I need a 1 there, so I multiply the numerator and denominator by 1/11. And when I do that, in the numerator I get 4 over 11, and in the denominator I get 1 plus, but I would really like that to be a minus, so I put minus -3. And then over here, I have x minus 3. I'm sorry, -3 over 11. And then over here I have x minus 3. If you distributed and did everything right now, the two expressions are still the same. But now you can see that your a value is 4 over 11, and your r value is -3 over 11 times x minus 3. And so then using that, you can create your series. Your first term is 4 over 11. Your second term is 4 over 11 times the -3 over 11 times the x minus 3. And then your next term is 4 over 11. Everything gets squared on that common ratio, so negative 3 over 11 squared, x minus 3 squared, and so on. You can write it in summation notation. And in summation notation, your first term is 4 over 11. Your common ratio is negative 3 over 11 times x minus 3. And the whole thing gets raised to the nth power, summation from n equals 0 to infinity. Interval of convergence, your common ratio is negative 3 over 11. So the absolute value of negative 3 over 11 times x minus 3 needs to be less than 1, which then means that multiplying both sides by 11 gives you that negative 11 needs to be less than, the absolute value of negative 3 is 3 times x minus 3. And that needs to be less than positive 11. So if we distribute, we get negative 11 is less than 3x minus 9, which is less than 11. And then if we add 9 to both sides, we get negative 2 is less than 3x, which is less than 20. And so then negative 2/3 is less than x, which is less than 20 over 3. And this is your interval of convergence. Okay, so in the previous section, we found that you can take a power series and differentiate it and term by term, and that the radius of convergence of the new series is the same. The interval of convergence may be different, but the radius of convergence is the same. You also learned that you could integrate term by term, and you get a power series whose radius of convergence is the same. And again, the interval of convergence might be different, the endpoints might change, but the radius of convergence is the same. Now, in this section, we figure out how to take a power function and make new power functions. So if you have a power function for f of x and a power function for g of x, then if you want to find a power function for f of kx, you just simply substitute in kx in for x, and so you end up with x to the n in your terms. If you want to find a power function for f of x to the n, well, then you just substitute it in, and so you get x to the n for your terms. You're just substituting in to your power function here, the x to the n. And if you have two power series that converge, they have to be convergent. And the limit laws allow you to take two series that converge and get a series for the then the sum will converge, and you just add them term by term, and that's all this says right here. If you know the power series for f of x and the power series for g of x, then the power series for the sum or difference is just the sum of the terms by terms. Okay, so we can use that to make new power series so that we don't have to start all over. So at the beginning of the section, you may have been wondering, why would I want to take a nice easy function like 1 over 1 minus x and write it in these complicated ways? Well, you'll see that it'll be useful to start off with those and generate some power series for some more complicated functions, which you're going to see in just a little bit. And we're going to use this to do that. So in exercises 19 through 28, use the power series that 1 over 1 plus x is 1 over 1 plus x. You can get this from the geometric series, like we did earlier, is the summation from n equals 0 to infinity of -1 to the n x to the n, as long as your common ratio is less than 1, to find a power series for the function centered at 0 and determine the interval of convergence. Okay, so what you should be prepared to do on an exam is I will just give you this formula right here and then ask you to find a power series for it using other known power series. And then what you are going to do is you're going to use partial fractions decomposition to rewrite it like this, right? And so then you can then use the geometric formula to find power series for the 1 over 1 plus x, that's this one right here, and the 1 over 1 minus x. Now, for the 1 over 1 minus x, for the 1 over 1 minus x, we don't have to go back to the geometric series. We can just use the series that we were given here, and we can just replace the x with negative x, right? And that's all we did is so the x gets replaced with negative x. So over here, the x gets replaced with negative x. And so this becomes the summation from n equals 0 to infinity of the -1 to the n, and we just substitute in negative x for x. But if you notice that because both of these have an exponent of n, we can factor out the exponent, leaving the base -1 times x, and -1 times negative x, and so then this just becomes the summation from n equals 0 to infinity of x to the n. Okay, now again, this you could also just get from the fact that this is what the geometric series looks like. This is the first one we talked about. If we replaced the r with x, we would end up with 1 over 1 minus x is this series right here. Or you can get it from this one, since we were staring at that one right now. I just wanted to go over how that substitution would get you that one. Okay, so then since this is just a constant and this is just a constant, then this right here is 1/2 times the summation of from n equals 0 to infinity of -1 to the n x to the n minus, and again we have a 1/2, and then the summation for 1 over 1 minus x is just x to the n. We can factor out the 1/2 since they both have a 1/2. And notice that then the only difference between the two is that this one is alternating and this one is not, and we are subtracting them. So when this is an even exponent, the coefficients will be opposites, right? So when n is 0, you get 1 for this one, and you get 1 for this one, and 1 minus 1 is 0, so that goes away. But when n is odd, like when n is 1, this is negative x, and this is still positive x. And so then, well, just go ahead and write out some of the terms and see how this looks. If you get stuck, that's what I like to do. So then this is 1 minus x plus x squared minus x cubed plus x to the 4th dot 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 minus, and then this one is 1 plus x plus x squared plus x cubed plus x to the 4th plus dot dot dot. And so then we get 1/2. The 1's go away. The x's become negative 2x. The x squareds go away. The x cubed becomes negative 2x cubed. The x to the 4th will go away. And then the odds will become x to the 5th minus 2x to the 5th. So all the evens will go away, and the odds will double up. And so then what you get is just the odds with it in there, and they're all negative. So what you get is negative 1 times, and when you distribute the half, then the 2's go away. And so you get negative 1 times x plus x cubed plus x to the 5th plus dot dot dot. And so then in summation notation, you have this negative 1 that you can take outside, and you have an x to the odd power, 2k plus 1, and you can start that at 0 and go on forever. Both of these converged, so notice that this is still geometric. Both of these converged for the absolute value of x is less than 1, so the interval of convergence doesn't change. This is still geometric. Your common ratio still needs to be less than 1, except now your common ratio is x squared. And so then x squared needs to be less than 1, so that means then that x needs to be less than 1 if you square root both sides of that. So the x squared needs to be between, so then, yeah, so x is still in between negative 1 and 1. Your interval of convergence doesn't change. Okay. So again, here we're trying to find the series representation for 2 over x plus 1 cubed, but they're telling us that one way to get to 2 over x plus 1 cubed is to find the second derivative of 1 over 1 plus x, right? And so then that means then that the second derivative of 1 over 1 plus x is 2 over x plus 1 cubed. So that means that the power series for this is the second derivative of the power series for this, right? Now, the 1 over 1 plus x, and we've already gone over that, is 1 minus x plus x squared minus x cubed plus x to the 4th. That was given to us, right? And so then the first derivative going term by term, now this term goes away. Then you get a negative 1 plus 2x minus 3x squared plus 4x to the third plus dot dot dot. The nth term will have become n times x to the n minus 1, and this goes on forever. Now then, when we take the second derivative, well, now this term is going to go away, and now we'll just have 2 minus 6x plus 12x squared and so then we will, for every term, we'll have brought down the n and the n minus 1, and then we'll have x to the n minus 2. But if we want to write that in summation notation, we can now write that in summation notation as a summation, and we'll start at 0 so that we can pick up this term. Go to infinity, and every term is going to look like this. N times n minus 1 times x to the n minus 2. I'm sorry, we can't start at 0. We have to start at 2. Because the first two terms went away. The first term went away here, the second term, the first term went away here, and then the second term went away here. And now let's check to see if that works, right? So when we start at 2, you get 2 times 1, x to the 0. So you will get your 2. Ooh, I'm sorry. It alternates, so we need an alternating factor. That's why it's important that we check. And it starts positive, negative, positive, so we have negative 1 to the, since we're starting at 2, and then we'll go ahead and make this negative 1 to the n, because we're starting at 2 and it starts positive. And so then, so we get our 2. Now when n is 3, this is going to be negative 1 to the third power is going to be minus, so that's right. And then we get 3 times 2 is 6, that's right. And then just x. And for the next one, negative when n is 4, then 4, negative 1 to the 4 is positive, that's right. And then 4 times 3 is 12, we got that. And then we take 2 away, 12 x to the 4 minus 2, x squared. And so that's working out. And that's how that goes. Now, if you wanted your series to start at 0, then you have to make some adjustments. So if we wanted to start this at 0, n equals 0 to infinity, then instead of having your first factor being n, I think you'd have to add 2 to it. And so you're going to add 2 to this. And then you're going to add 2 to this. And then don't forget your factor of negative 1, which I had forgotten, to the n. Now when n is 0, this is going to be 1, this is going to be 2, this is going to be 1. 2 times 1 is 2. And then x squared. I'm sorry, x to the 0, which is just 1. And then when n is 1, then this will be -1, and this will be 3 times 2, which is 6, and this will be x to the first power. And there we go. That's how you can change your limits there. Don't care if you do or if you don't, but you need to be careful when you take derivatives because you lose terms. And so we didn't start at 0 anymore. We lost the first two terms, so we started at 2. Okay, so again, we want to find the natural log of 1 minus x squared. And here they're telling you how to do that, but let me show you where this came from, right? And this came from the fact that the natural log of 1 minus x squared can be rewritten as the natural log of 1 plus x times 1 minus x which we could then rewrite this as the natural log of 1 plus x plus the natural log of 1 minus x. But we know the series for the 1 over 1 plus x. And so how we could get here is by integrating 1 over 1 plus x. And how we could get here is by integrating 1 over 1 minus x, except that then that is going to give us a minus here when we integrate it. And so that's how they came across. That's how they came up with this, right? So if you integrate this, you get the natural log of 1 plus x. If you integrate this, you'll get minus the natural log. I'm sorry, you'll get plus the natural log of 1 minus x, and then that equals this, and this equals that. So then, if we know what 1 over 1 plus x is, 1 over 1 plus x is the summation from k equals 0 to infinity, I'm sorry, n equals 0 to infinity of x to the, I'm sorry, -1 to the n, x to the n. So if we integrate both sides of this equation, then we, on the left, we get the natural log of 1 plus x. And on the right, we just get summation of add 1 to the exponent, divide by the exponent, and then you have -1 to the n is just a constant that doesn't change. So you just integrate term by term. So each term you're going to add 1 to the exponent, divide by the exponent, and here you're not losing any terms because you're integrating. But you do get an extra term because you have to plus c. But if you put in 0 for x, then this sum is obviously 0 because everywhere you see an x, you put a 0, and you have an x in every term, even for 0. And if you put 0 for x on the left, then on the left you get the natural log of 1, which is also 0, which allows you to find that your value of c is 0. So we don't need the plus c because the value of c is 0. Likewise, we know that the 1 over 1 minus x is the summation from n equals 0 to infinity of 1 over 1 minus x. I'm sorry, of x to the n. So we know this series from the previous problem. And so then if I integrate this, I can find a series for this one. And so then the series for, I'm sorry, if I integrate on the left, I get negative the natural log of 1 minus x. And so then integrating term by term, then I get the summation from n equals 0 to infinity, add 1 to the exponent, divide by the exponent, plus c. And again, if I put 0 in for x on the left, I get the natural log of 1, negative the natural log of 1, which is 0. And if I put 0 in for x on the right, I get c. So c is 0. We can ignore the c. And so now the natural log of 1 minus x squared is just the sum of these two. Oh no, I'm sorry. So the natural log of 1 plus x is equal to okay, yeah, so when I integrated this, I got this. And yeah, so now all I'm supposed to do is add those two together because that's what they told me. Yeah, so when I add these two together, I get the natural log of 1 minus x squared. But again, if you write out the terms, you can see a nice pattern. This one is going to be starts out positive, x to the first plus x squared over 2, sorry, minus because it's alternating, plus x cubed over 3 minus x to the fourth over 4, and so on. And then, so for this one, you're going to get x to the first over 1 plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. And then you can see that all the even ones are going to cancel out. And so you're just going to get x plus 2x cubed over 3 plus 2x to the 5th over 5, and so on. And so then in summation notation, this will be the summation from n equals 0 to infinity of x to the 2n plus 1. We only have odds, and we divide by 2n plus 1. And it's alternating, so we need this. Oh no, it's not alternating. Right, all the negatives canceled out. It's only positive terms. And so there we go. For the interval of convergence, both of these have an interval of convergence of, a radius of convergence of 1. And so then all we have to do is check the endpoints, check the -1 and the 1. So when x is 1, you get 1 over 2n plus 1, which diverges because you can see that that's 1 over 2n plus 1. You can compare it with the limit comparison test with 1 over n. And when x is -1, 2n plus 1 is odd, and so it's not alternating. It's always a -1, and so then that one also diverges. So the interval of convergence is from -1 to 1. I believe I forgot the interval of convergence on this one. Okay. But yeah, this is a geometric, this is still geometric. And so since it's geometric, your R value still has to be between -1 and 1. So x squared needs to be between -1 and 1. And so then that's the same interval of convergence. Okay. So on this problem, they did not give us a hint. They did not tell us how this function is related to the series that we've been looking at before, right? But using first semester calculus, we can find the derivative and know then that this is x squared plus 1 times 2x. And so then what that tells me is that my function is the antiderivative of 2x over x squared plus 1. And so then what that tells me is if I can find a power series for 2x over x squared plus 1, then I can integrate it term by term and get a power series for the function I was given. Right. So to begin with, we can find a power series for 1 over 1 plus x squared by noticing that all you've done is you've replaced the r with negative x squared. So then this is, so the formula for the geometric is 1 over 1 minus r, and all you've done is replaced the r with negative x squared. That's how you ended up here at this positive x squared. And so then that tells you, that gives you a power series for this. And so then what this is 1 minus x squared plus x to the fourth minus x to the sixth, and so on. In summation notation, this is the summation. It's alternating, negative 1 to the n, and then x squared to the n, or x to the 2n, and summation from n equals 0 to infinity. If we then multiply both sides of this equation by 2x, and then what you will get is 2x minus x squared times 2x. So then that'll be 2x cubed plus 2x to the fifth minus 2x to the seventh. And then in summation notation, this will just be the summation from n equals 0 to infinity. It's still alternating, that multiplying by 2x doesn't change that. And then we just get one factor of 2, which we can put on the outside or the inside, makes no difference. And then x to the 2n plus 1, because you just add the exponents, and if you notice, that happens, right? So then if we now integrate both sides term by term, on the right we integrate term by term. Then on the left, as I just showed you, the derivative was 2x over x squared plus 1. So on the left, we get the natural log of x squared plus 1. On the right, when we integrate, we get this constant of integration, which is c. And then if we integrate term by term, we still have this factor of 2 that we can just leave on the outside. And the negative 1 factor, that's a constant for each term, so that still just stays there. Add 1 to the exponent, and so you will get x to the 2n plus 2. Divide by the exponent, and you will get 2n plus 2. And then you still have the summation from n equals 0 to infinity. But again, when x is 0, then the summation part is 0, and all you have is c, and when x is 0 on the left, you get 1, so then there is no c. Your c goes away. And there you go. That is your interval. I'm sorry, that is your power series. Now for the interval of convergence, again, all you have to do is check the endpoints. You don't, when you multiply the interval of convergence of this, the radius of convergence was 1. So it was from negative 1 to 1, it converged. When you multiplied it by 2x, that didn't change the radius of convergence, so you still just have to check 1. And when you plug in either 1 or negative 1, you end up with the series from n equals 0 to infinity. 2 is out here, and 2n plus 2 is always going to be an even number. And so with an even number, 1 to an even number is going to still be 1, and negative 1 to an even number is still going to be 1. So in either case, you end up with negative 1 to the n over 2n plus 2. Now this converges by alternating series test. So your interval of convergence is from negative 1 to 1. And there we go. Okay, so find a power series for f of x equals 1 over x, centered at x equals 1. Okay, so again, you have 1 over x. That means you want to make your r look like x minus 1. So again, we'll put parentheses right there. And we want an x minus 1. But then we have to add 1. And again, this is 1 over 1 plus, this is 1 over 1 minus negative 1 times x minus 1. Right? Those two expressions are the same. And so then we can, your a is 1, your a is 1, your common ratio is negative 1 x times x minus 1. And so then you can write this in summation notation, summation from n equals 0 to infinity of 1 times negative 1 to the n x minus 1 to the n. And there you go. We are going to need that for the next one. So find a power series for f of x equals the natural log of x. Well, then the natural log of x is equal to the antiderivative of 1 over x dx. But the antiderivative, but 1 over x, we just found a power series for that. And the power series for that is negative 1 to the n x minus 1 to the n. And so then, integrating term by term, we're going to get a constant, and then we're going to get summation from n equals 0 to infinity. We're going to have this negative 1 to the n. We're going to add 1 to the exponent. Divide by the exponent. And that's it. Plus c. But again, this is the natural log of x, and the natural log of 1 is 0. When we plug in 1 in for x, every term here goes away, so this c goes away again, and there's no constant of integration. And those two formulas are exactly the same. Now for your interval of convergence, if n is, so this is we need to figure out what is the interval of convergence, right? And so we didn't do that on this problem over here. So let's go back over here. So your common ratio here was x minus 1, and so then the absolute value of x minus 1 needs to be less than 1. So then negative 1 needs to be less than x minus 1, which needs to be less than 1. So 0 is less than x, which is less than 2, right? So this is your interval of convergence, IOC. And on this problem, here's my new series, and the interval of convergence has the same endpoints, but it may or may not include the endpoints. So my interval of convergence here, IOC, still goes from 0 to 2, just like it did over here, from 0 to 2, but the endpoints could change. Now when I put in 0, I get if x equals 0, I get this series. Negative 1 to the n times negative 1 to the n plus 1 over n plus 1. And so then that becomes the series negative 1 to the 2n plus 1, all divided by n plus 1. And negative 1 to the 2n plus 1, 2n plus 1 is always odd. That's just going to be negative 1. So this is just negative 1 over n plus 1, which is the harmonic series which diverges, right? So that diverges. But if x equals 2, then we get this series. Put in 2 for x right here. 2 minus 1 is 1. 1 to any power is 1. And you get negative 1 over n plus 1. And that converges because it's an alternating series. And so this is your interval of convergence. Okay. And so now, so we know that this series converges for 0 and 2. It's so then, I'm sorry, it converges for every number between 0 and 2, including 2, not including 0. And so now, if we substitute in 2 on the left and the right, we get that the natural log of 2 is equal to the summation from negative 1 from n equals 0 to infinity, negative 1 to the n over n plus 1. And if you plug that in, what you get is 1 minus a half plus 1/3 minus 1/4. This is the alternating harmonic series. We knew that that converged before, but we didn't know what it converged to. And so now we'd see that it converges to the natural log of 2. And so the exact value of 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 is the natural log of 2. So I just thought that was kind of neat that we can now figure out what that sum is, and that simple looking series adds up to the natural log of 2. Okay, so find a power series representation for f of x equals 1 over 1 plus x squared, centered at x equals 0. So you can see that if we just replaced the we can look at this as having replaced the r with negative x squared, and so then we would replace, and the a with 1, and then 1 over 1 plus x squared is then 1 minus x squared plus x to the fourth minus x to the sixth, and so on. In series notation, this is the summation from n equals 0 to infinity of negative 1 to the n power, and then x squared to the n power, so x to the 2n. The interval of convergence, this is going to converge whenever your common ratio x squared is between negative 1 and 1. And so then this means then that x needs to be between negative 1 and 1 at either of those endpoints, and that does not converge. And so now we can use that to find a power series for the inverse tangent of x, because we know that the inverse tangent of x is equal to the antiderivative of 1 over 1 plus x squared. But we just figured out a power series for 1 over 1 plus x squared was the summation from n equals 0 to infinity of x to the 2n and we can integrate it term by term. We're going to get this constant c plus the summation, which is integrated term by term. Oh, I forgot the negative 1 to the n. So you're just going to add 1 to the exponent, x to the 2n plus 1, divided by the new exponent, 2n plus 1, and then you still have the negative 1 to the n. If you put in 0 in for x, the inverse tangent of 0 is 0, and on the right, the summation becomes 0, so then that means the only way that works is if c is 0. So now you have a series for the inverse tangent, right? And so then this is how your calculator knows how to find inverse tangents. It doesn't have all these inverse tangents memorized. It has this infinite polynomial, x to the 2n plus 1 over 2n plus 1. And it plugs them in here, right? Okay, now interval of convergence. We knew that the interval of convergence for this thing was from negative 1 to 1. We know that the radius of convergence is going to be the same for this one when we integrate it, but the what may change is the endpoints. When at 1, you're going to get if x equals 1, you get this series, negative 1 to the n. 1 to any power is 1, so you end up with this, and this converges by the alternating series test. If x equals negative 1, then you get this series. So here you'll have negative 1 to the 2n plus 1, and then here you'll have negative 1 to the n, so you're going to end up with negative 1 to the 3n plus 1. And 3n plus 1 is even when n is odd. If you put in 3 times 3 is 9, but then you add 1, you get even. And it's odd when n is even. 3 times 2 is 6, plus 1 is 7. So all this does is alternate. So this also converges by the alternating series test. Okay, so then your interval of convergence for this is from -1 to 1. So your power series here converges to the inverse tangent of x. Right? And so find the exact value of 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, right? If you look over here at our series, when you plug in 1, it's going to alternate, and the numerator will always be 1, and then this is from n equals 0 to infinity. And so the denominator is just the odds. So this is just the inverse tangent of 1. And the inverse tangent of 1 is pi over 4. And so this series here converges to pi over 4. And if you multiply that by 4, both sides of that equation by 4, then 4 minus 4/3 plus 4/5 minus 4/7 plus 4/9 dot is exactly pi, which I think is kind of cool. Okay, so there's your homework for this section, 3 through 25 odd, and 37 and 39. So this will be due next Thursday. I will host office hours during class time. I'll post them. I'll start the conference at 6. Give some of you a chance to get home and from work and eat. And I'll answer any questions you have on this section. This will be due next Thursday. Good night. Stay safe.